Good evening, everyone, and welcome to the Amateur Radio General Class, session number 18. During our previous session, we looked at our question pool review that we would normally review all of the theories from our previous session. We also looked at the concept of critical angle. Then we discussed what the skip zone was. Also, scatter propagation. We reviewed once again the concept of Envis, or near vertical incidence skywave. Then we talked about the notch filter, the IF shift, as well as the attenuator features on a radio. Also, we looked at the noise blanker, noise reduction, and then we went on to discuss what the electronic keyer was. Also, reverse sideband when it comes to CW operation. Split operations, we looked at the feature called the dual VFO. We also discussed what the ALC was. We also contemplated what happens when stray RF or stray radio frequency gets from a transmitter into an audio cable. We then went on to discuss linear amplifiers, the vacuum tube type, as well as the solid state. And then we went back to ALC again, from a practical standpoint between a radio and amplifier. And then we also discussed the time delay feature. And then we ended with the topic, again discussing antenna tuners. When we look at our curriculum, we see that we are progressing quite nicely, and we are on the topic amateur radio practices. So just after this, 3 more topics to the end. Again, a reminder to participants, consider taking those practice exams. It will tell you where you are at, even though we are not yet quite finished with the material and the course. It does give you a good idea and build confidence. Again, you may know a lot more than you think. We had no outstanding questions from the previous session. So we go straight into, as we have grown accustomed to, our question pool review. And on our question pool, we use our no-nonsense guide. And we are on page 56 for those persons that are following on the PDF copy of the No Nonsense General Class License Study Guide. So we go straight into the questions in the question pool, and we will speed through them, seeing that all of the theory we covered during our previous session. Let's go. First question. What does the term critical angle mean as used in radio wave propagation? So we said that that was the angle that the radio wave leaves the antenna and goes off towards the ionosphere, right? So the answer is, it's the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So remember that critical angle? Anything above that, it's going to pass straight through, and it's not going to be bounced, it's not going to be reflected, or it's not going to be refracted. So your takeoff angle is very important, and that critical angle is the one where you need to be below that. Next question in the question pool. What type of propagation allows signals to be heard in the transmitting skip zone? So you may recall that we defined the skip zone last session. We showed where it's located. It's beyond where the ground wave reaches, and it is before where the signal that goes via the skywave bounces back to Earth. So that's that dead zone, we also called it, yes? And we showed that there are a couple of ways or a couple of techniques to still communicate in that skip zone, and one of the ways is that signal returning via scatter propagation. So that's the answer, scatter. Next question in the question pool. Why are HF scatter signals in the skip zone usually weak? So again, it refers to what we just talked about. it's a scatter propagation that's coming back from our signal that has already bounced off the ionosphere. It's coming back at us. And as a result of that, only a small part of the signal energy is actually scattered into the skip zone. That's why the signal is weak into the skip zone. Okay, moving right along. What is a characteristic of HF scatter? So because it's a weak signal and so on, and you hear it sounds very wavery. So the answer is they have a wavering sound. That's how you know you're receiving a signal via HF scatter. Next question in the question pool. What makes HF scatter signals often sound distorted? So recall when we showed the diagram of that scatter propagation, when the signal goes back in the opposite direction, it's arriving via different paths, slightly different paths. So that is exactly what is happening. The energy is scattered into the skip zone through several different radio wave paths. And that's why, because you have several of those signals reaching, the audio sounds distorted. Okay, so if you need a review, just kindly review the question pool, the slides from the previous session or the video recording. Next question. What is Envis, near vertical incident skywave propagation? So we had discussed Envis ad nauseum, and we learned that Envis is short distance MF or medium frequency or HF propagation using high elevation angles. Remember we showed how Envis is achieved, the technique. We try to send the signal straight up into the sky so that when it bounces or it drops shorter than it would when you have a lower angle. Okay, let's continue. Next question in the question pool. What is the purpose of the notch filter found on many HF transceivers? So you may recall that we discussed that feature called the notch filter. We said it notches out interference, and we said it's like, talk to the hand. We're just basically ignoring that section that is the interference piece in the IR stage. So that is exactly what the notch filter is, or what it does. It is to reduce interference from carriers in the receiver passband. So let's go with the next question. Which of the following is a use of the IF shift control on a receiver? And remember, IF is not the word if, it is intermediate frequency. So what is the use of IF shift on a receiver? Again, similarly, we're talking about trying to avoid interference, and we sort of shifting the IF frequency just slightly away from the interference. However, we're still maintaining look at the signal itself that we're interested in. So that's what the IF is about, and we use it to avoid interference from stations very close to the receive frequency. Let's go to the next question. What is one reason to use the attenuator function that is present on many HF transceivers? So they're asking us about the attenuator function. Remember we said attenuation is reduction. So let's see what the answer is. Purpose of the attenuator is to reduce signal overload due to strong incoming signals. So if you have a radio operator who's close by, very near to us, and that is overloading your front end and your radio, and you want to reduce that overload, you use the attenuator function. Press the button, push the button, turn it up. Okay. Next question in the question pool. How does a noise blanker work? So we had showed a diagram of what noise looks like on a graph. It was pulsing signals along with our valid signals. And we said that we have a technique called a noise blanker feature circuit that will look at those pulses, and it will reduce the signal at the point of the pulse and allow you to hear the rest of your signal. So it just takes care of those little noise pulses. So how does it work? By reducing the receiver gain during a noise pulse. So it essentially reduces that noise, so you almost don't hear it, and you will hear your valid signal. Next question in the question pool. What happens as the noise reduction control level in a receiver is increased? Right, so that's another feature, noise reduction. And we have said with noise reduction, sometimes your signal might sound a little distorted, and that's the answer. Received signals may become distorted. That's with noise reduction feature. Next question in the question pool. What is the purpose of an electronic keyer? So remember we said we use the electronic keyer for Morse code or CW being continuous wave. So the purpose of the electronic keyer is the automatic generation of the strings of, they say, dots and dashes. We may say dits and das. Strings of dots and dashes for CW operation. CW being continuous wave. And sometimes we say Morse code because they sort of go hand in hand. That's how you do Morse code, using CW, continuous wave. Next question in the question pool. What is one advantage of selecting the opposite or reverse sideband when receiving CW signals on a typical HF transceiver? Do you remember we said we may be using the upper sideband part of when we are listening to CW signals? I know someone put in the last time, it's really the CW knob. You go to the CW position. It is, right? When you are receiving, however, you need to be aware that it's a bit different in that sense. So that was a good point. I think it was Ramzan who raised the last session. However, we can do that reverse sideband feature where we go from upper sideband to lower sideband on the receive. And what it may do, it may be possible to reduce or eliminate interference from other signals because we're just shifting. Remember we showed the graph that shows where you have the carrier, you have the upper sideband, the lower sideband feature. It's slightly to the left, slightly to the right of the signal. So if the interference is to the right on the upper sideband, you could probably select lower sideband and therefore you avoid that bit of interference or heterodyning or that noise or tone that you might hear on one part of the sideband. You can just switch it. So yes, it is CW that we're talking about. All right. Next question in the question pool. What is normally meant by operating a transceiver in split mode? So we said that split mode is a mode where two different frequencies are used and is often used by DX or long distance or foreign stations when they're working a pileup. Many persons trying to get to that rare DX station. So what is normally meant when we are operating in split mode? It means that the transceiver is set to different transmit and receive frequencies. Normally on HF you would be operating on the same frequency for transmit and receive. However, split mode is actually using a different transmit and a different receive. Remember we said something like 5 up? Right. Okay. Which of the following is a common use for the dual VFO feature on a transceiver? So what is a common use of dual VFO? It is to permit monitoring two different frequencies. If you have two different VFOs or two different dial gauges that you can dial up frequencies on, and you have a dual VFO feature, variable frequency oscillator is what VFO stands for, you can monitor dual frequencies or two frequencies at the same time. Feature in the more expensive rigs. Again, you get what you pay for. All right, let's go again. Next question in the question pool. What is likely to happen if a transceiver's ALC system is not set properly when transmitting AFSK signals with the radio using single sideband mode? All right, so let's dissect this question a little bit. They're asking us what is likely to happen. So we're talking about the ALC system if it is not properly set or it is not properly adjusted when you're transmitting AFSK signals, audio frequency shift keying signals, meaning digital signals, with the radio in single sideband mode. So what happens if you have your ALC incorrectly set or you have the wrong ALC setting? That is what is the question asking you when you're doing digital modes and the radio is in SSB. Well, we learned that you can have distance, you can have signal distortion, and you can cause spurious emissions, which is our answer. Improper action of ALC distorts the signal and can cause spurious emission. So as hams, we need to learn to set our ALC correctly. Next question. Which of the following can be a symptom of transmitted RF being picked up by an audio cable carrying AFSK data signals between a computer and a transceiver? All right, so this is asking the question about stray RF. That was the topic on the slide in the slide deck. when we saw that the radio frequency from our radio or antenna could get back or could be picked up by an audio cable. Yes, so that is what we're referring to, stray RF. What happens when that occurs? The transmitted RF is picked up by an audio cable. So for example, the interface cable between your computer, your laptop, and your radio doing digital modes. What if that acts as an antenna and picks up the RF signal, that audio cable going between the radio and the interface, the laptop or the computer and the radio or the transceiver? If that picks it up, what happens? Well, all of the following choices are correct. The VOX, voice-operated circuit, will or does not unkey the transmitter, meaning that that RF is coming in to the signal and it keeps the radio keyed up or in transmit mode. That is one of the symptoms when you have that stray RF that comes in to your audio cable. Also, the transmitter signal becomes distorted. Right? So the person will tell you you're sounding distorted. So that could be one of the symptoms when someone tells you that you know the signal is not decoding properly. When they look at it, your signal appears distorted on their waterfall or on their scope. Also, you can have frequent connection timeouts, meaning it's connected 1 minute and then it's not connected again. So those are the symptoms of stray RF. Next question in the question pool. What is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? Okay, let's dissect this question a little bit. What are they asking us? They're asking about the correct setting, the correct adjustment. But of what? The load control of a tube amplifier. So what is the correct adjustment? Well, we said last session, we showed a gauge, we showed what the amplifier looks like, we showed the control, and we said that when it is correctly adjusted, when that load control or the coupling control is correctly adjusted for your tube amplifier, you will get maximum power output, but without exceeding the maximum allowable plate current. That is the correct adjustment for a tube amp with the load or coupling control. Next question in the question pool, again sticking to vacuum tube RF amplifiers. What reading on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? So let's dissect this question. What are they really asking us? Well, they're talking about a tube amplifier. That's what we're referring to. Not a solid state, it's a tube, vacuum tube amplifier. So that's what we're talking about. And they're asking us what reading on the plate current meter. So remember we showed last session on our slide in the slide deck. We saw the plate current meter, what it looks like, little gauge. All right, what indicates the correct adjustment? How do you know that you have that properly, that plate tuning control? Remember we showed a knob called the plate control or plate tuning control. How do you know you have that correctly set? Is it by VAPS, as we say? Or do you just turn it and hope for the best? No. What you do is as you turn that tuning control, that plate tuning control, you will see a pronounced dip. The needle on the meter will be going up, going up, going up, and all of a sudden you'll see a little dip down. That is the point of correct adjustment. Let's go. Next question in the question pool. What is a reason to use automatic level control with an RF power amplifier? So what we showed is that you have your transceiver, your radio, and you had your RF power amplifier, and there's a connection called the ALC, automatic level control, that you connect your radio or your transceiver to your amplifier. So why do you use it? You use it to reduce the distortion due to excessive drive. So that ALC control will tell the radio back off your drive a little bit automatically. It's an automatic level control. Stops the distortion due to excessive drive. All right, let's continue. What condition can lead to permanent damage to a solid state RF power amplifier? Okay, so it's a short question, but let's dissect it a little bit. This time we are not talking about a tube amplifier. We are talking about solid state. Okay, so what condition can lead to permanent damage? So we said that if we drive too much power from our transceiver to the amplifier, we could damage it. And that's the answer. Excessive drive power. But that excessive drive power is from the radio transceiver or the transmitter that is connected to the amplifier. We're sending too much power from that radio to the amplifier, and we can damage it if it's an RF, it's a solid state power amplifier. Next question. Why is a time delay sometimes included in a transmitter keying circuit? So remember we said that that's a feature. Sometimes you have a little time delay. And the reason we have it is to allow time for the transmit-receive changeover operations to complete properly before RF output is allowed. So that's the purpose of the time delay. Last question before we go into our slide in the slide deck. What type of device is often used to match transmitter output impedance to an impedance not equal to 50 ohms? So remember we keep saying hams are matchmakers. So let's dissect this question a little bit. It's a matchmaker question. What type of device? In other words, what's the name of the device? That's what they're asking you. So you have to, the answer is a name of something. What type of device? But used to what? To match transmitter output impedance to an impedance not equal to 20 ohms. What is that impedance they're talking about? Most likely it's an antenna. That is where you have a transmitter going typically to an antenna. I mean, you could go to a dummy load, you could go to other things, in test instruments. But typically, your transmitter or your transceiver is being connected to an antenna. So what they're asking you here, what device do you use to match a transmitter to an antenna? And as we learned ad nauseum in our course during our technician class as well as general class, we said hams are matchmakers and we use antenna tuners. So that's the answer. Antenna coupler, or also called an antenna tuner. And that's it for the questions in the question pool. Let's now go back to our slides in the slide deck. Right, so that's it for our question pool review. Let's do a couple slides before we take our break. So, we are at the point where we are going to discuss some test equipment. And the test equipment that we are going to talk about first of all is called the voltmeter. But what exactly is a voltmeter? On the right hand side, we have a couple of examples of what it looks like. Now, sometimes you may hear people talk about a VOM or VOM. They may call it a multimeter and so on. But for the purpose of our exam, we are calling it a voltmeter. Some of these meters, of course, will have multiple functions. It will not only measure voltage, as the name is suggesting. It will measure current. It will measure several other things as well, resistance, and so on. However, this is an example of a voltmeter on the left-hand side. On the right-hand side, we also have an example of another voltmeter. One is analog. As you notice here, you have the readings, and then you have a needle, and that needle moves. That's the analog type. And then on the right-hand side, you have the digital meter. You have digits, a readout. I mean, you have a bar graph below here, but it's a digital multimeter or digital voltmeter. On the left-hand side here, we have the analog. So just note that there are two types, and each of them, of course, come with their own advantage and disadvantage. So you have the analog voltmeter, and you have the digital voltmeter. And keeping it real, this is what it actually looks like. We have a little diagram here in the middle that shows you how you use it. So you have a circuit here. So you have probably a resistor in a circuit. You have a battery or a voltage source. You have a resistor, and you want to measure the voltage drop across the resistor. This is your trusty meter. You have our two leads. You have your leads across the resistor, and you will measure your voltage, for example. So this is how you actually use your test instrument in a circuit. Our little circuit on the right-hand side, very basic circuit, a battery or voltage source, and a resistor. You measure it using the leads, and the instrument will give you the readout. So these are the meters that we have, and we need to know a couple things about them for the exam. So the first thing we need to know that the analog voltmeter, this one on the left-hand side, might be preferred when you are adjusting tuned circuits. Remember, tuned circuits are circuits that will have things like capacitors and coils. We learned that in the technician class and some slides in our general class. So if you're adjusting tuned circuits, you may prefer an analog meter. Now, they don't specify in the theory exactly why, but just give you something extra. The nice thing about it is sometimes you need to see when something twitches. Remember we said when we are doing the plate current, You just want to see when there's a pronounced dip. Sometimes it's harder to tell when something increase or decrease on digital displays like this. But on a display where you have a needle and you see the needle going back, going up, going up, going up, and then all of a sudden it dips down and then goes back up. Sometimes you need to have that visual indicator to know, yes, there was a little dip or a decrease at a point in time. So that's why, even though analog, some people say digital is always better, but there are advantages and there are times when analog comes in very handy. It's very difficult. So everything doesn't replace everything. You sometimes have better, yes, but sometimes you have features of other technology that works for you. So you need to know for the exam that an analog voltmeter may be preferred when you are adjusting tuned circuits. However, digital voltmeters tend to give you better precision. Notice the number of digits. You could say 1.0090 volts, for example, if that's what that readout said. That'll be a lot harder to read that out on an analog display. So we say that digital voltmeters give you better precision. You have a number of digits and you can get a very nice figure precision. Also, another advantage of these digital types of meters is what we call the input resistance. Notice in this circuit here, I'm putting a meter across my circuit. Guess what? This meter, when I put it into the circuit to measure this voltage drop across the resistor, I'm also introducing some resistance that comes with the meter. So I don't want that to be a large resistance at all. Otherwise, I might get an incorrect reading of the voltage drop across here. So what I want is a very high input resistance. And that's one of the advantages of a digital meter. If you use it, you have a high input resistance compared to an analog meter, and that's an advantage, or it's considered an advantage of a digital voltmeter. So when you put that into a circuit like that, the loading is much less when you're measuring a voltage drop across this resistor. You can safely ignore the presence of the meter. The meter doesn't measurably affect it. So you can take it as gold, whatever value you get here. But if you use an analog meter, that might influence the circuit a lot more. And you have to take a little bit of grain of salt as the reading, because the voltmeter is presenting a lower resistance and it is causing a little more load to go through the meter. And you really don't want to do that. You want this thing to be a fly and you want to just observe. But the reality is we're doing electrical measurements and your instrument is going into the circuit. It's not passive at all, it's active, and it's going to take up some of the current that flows through as well. So that's why you want your digital voltmeter as opposed to the analog meter. That's the advantage. And we have those points here that is listed in the bullet points, and you need to know all of these things for your exam. So at this time, folks, we'll take a short 2-minute break. And please get up, take a little stretch, have some water, have a bathroom break, and we'll be back in about 2 minutes time. Okay, welcome back everyone. So we have a question. Ramzan asks, which one of the testers is best to test MOSFET? So of course he's asking, should I use an analog meter or a digital meter? So it's fine. You can use digital meters. As a matter of fact, that's what I would typically use. So I would say go with the digital meter when you're testing your MOSFET. All right, excellent question indeed. So continuing, we are still discussing test equipment. And one of the pieces of test equipment that's really, really handy for an amateur radio operator to have is called an oscilloscope. And if we look on our right-hand side here, we'll see what an oscilloscope looks like. Of course, you have the modern ones with the LCD screens, and then you have the slightly more vintage ones with the CRT, cathode ray tube type displays. However, they all function in a very similar way. So this is what an oscilloscope looks like. You have inputs, and one of the input will be what you call a horizontal channel, and another input will be a vertical channel. Why one is horizontal and one is vertical? Because if you were to look at the oscilloscope, you'll notice just like a graph, you have a y-axis and you have the x-axis. So you need an input for the vertical axis and you need an input for the horizontal axis so that you can get a display like this, right? So that's an example of what an oscilloscope could be used for. Of course, you have single channels and operation and so on. But the idea is that typically you have a horizontal channel and a vertical channel. And the channel amplifies the signals and displays it on your screen for you. So you can see visually what a signal looks like. So that is how sometimes you can visualize a signal, whether it's an audio signal, a speech, whether it's a tone created by your computer for your transceiver, or whether it's your RF, the radio frequency that's transmitted from your radio, you can use an oscilloscope to monitor. Of course, like every other instrument, you have to be very careful that you don't overload it with a signal. And we'll be coming in a little while as to some of the techniques that you use. Some of these instruments are very sensitive. So if you have very strong transmitters, you can't just simply connect a transmitter into your oscilloscope and so on. But it's a really good tool that allows you to observe complex waveforms, things that you would not otherwise be able to observe. You can't just put your voltmeter on it and see what that waveform looks like, compared to an oscilloscope where you have a nice graphical display as to what the waveform looks like. The voltmeter will probably tell you what your voltage is at any point. You'll see it changing up and down, but that doesn't really give you an idea what it looks like. Is it constant? Is it changing? Is it sinusoidal? Is it square? What is its shape, you know? So the oscilloscope and its variants will allow you to visually observe what your signal looks like. And you can take measurements as well, because the gratitude is actually calibrated and you can see what value is by looking, okay, this is the peak of this waveform, and you just know what that value is from its calibration, and you can say, okay, that's the voltage or that's whatever it is. You can take measurements as well very accurately also. And some of the better oscilloscopes, you'll be able to display a lot of values as well on the screen, and you can even have a little table or tabular format of some of those values, the peak values, and if you have more than one peak value. So a very handy, lovely piece of equipment. If as an amateur radio operator, you can have that as part of your tool and the toolkit, very, very handy. So this is what an oscilloscope is. However, what's one of the uses for the oscilloscope for practical use in amateur radio? So when we're using CW, continuous wave, or sometimes we'll say Morse code, right? You have your transmitter that is transmitting Morse code, but you want to see whether you have a clean Morse code signal. Your electronic keyer, your transceiver is generating a really nice signal for Morse code, for CW. You can use your oscilloscope to monitor that waveform. So that's the second bullet point here. One of the best uses in amateur radio for an oscilloscope is checking your keying waveform for a CW transmitter. And on the right-hand side bottom here, you see what a CW signal might look like. You have the rise time, you have the signal, and then you have the fall time. So just observing that could tell you whether you have a nice clean CW signal or if it's somehow distorted. You're monitoring it. You don't necessarily have to get feedback from someone external, the other receiver, the person, the amateur radio operator that you're communicating your Morse code signal or your CW signal to, and they'll tell you, well, you know, it's not as clean. You could monitor it for your own self and see how you are likely to be sounding. Now, the other point here at the bottom here is what we talked about, a bit of safety about, given that the price of an oscilloscope is very high, usually, you don't want to blow your oscilloscope by connecting your transceiver straight into your oscilloscope and then ping, that's it for the amplifier section, it's gone. So what you have to do, yes, you can measure RF using your oscilloscope, but you have to make sure that you use something called an attenuator, and you have to make sure that you're using the correct attenuator. Sometimes what you can do is you can transmit into a dummy load, and some dummy loads will actually have a tap off of that dummy load, which is an attenuated signal, and then you may still pass it through an attenuator, and then you go to your oscilloscope. So again, before doing something like this, you have to know what you're doing. You don't want to damage your equipment. And that's the last point here, and the bullet point here, that you need an attenuated RF output of the transmitter as the signal source to connect it to the vertical input when checking the RF envelope pattern of your transmitter. So you need to know this for your exam. It needs to be attenuated RF as the signal source, and you need to connect it to the vertical input, the vertical timeline, the vertical input on the oscilloscope, so that you can check the RF envelope pattern of your signal. Okay, continuing, another piece of test equipment, very popular in the amateur radio world. Very good to have. Once you're doing antenna tuning, once you're constructing building antennas, once you're putting up your station, whether it's at home, whether it's for portable operation, you're going somewhere, it's really handy to have some sort of antenna analyzers. Because quite frankly, you can have the best radio in the world, the best transmission line in the world, best power supply in the world, best amplifier, best antenna tuner. But if your antenna itself sucks, well, there you go. So we need to analyze our antenna, right? And what do we use? We use, one of the things we can use anyway is called an antenna analyzer. And it is an instrument that amateur radio operators use to measure the performance or the properties of that antenna, as well as the feed line. Yes, it can measure certain things about your feed line or your transmission line. We'll come to that in a little bit. But one of the things that it measures really nicely for an antenna, you have a given antenna and you have your antenna analyzer. And we have a trusty diagram here that shows, for example, how you will connect your antenna analyzer. So on the right-hand side, we show an example of what an antenna analyzer might look like. You notice you have a lot of knobs, you have some gauges, you have a display that displays a number of things like SWR, and you have connectors to connect your antenna to. So this is, for example, how you will use an antenna analyzer. Your antenna analyzer, you have a bit of coax cable, for instance, that goes to your antenna, and you can measure the standing wave ratio. Remember, we had discussed that. It's important to have a low SWR for your antenna. So you can measure for a particular frequency. That's what these knobs do. These knobs select a frequency, and you can adjust what frequency. This particular antenna analyzer is showing it's on the frequency 14.339 megahertz. And I want to know what my SWR is at that frequency for this particular antenna. And look at it, very nice SWR, 1.4 to 1. So that's a relatively low or pretty good SWR for an antenna. So if my antenna is too short or too long, it will show up with a high SWR. You have other things that you will see about the antenna as well, the impedance, reactor, several other things as well. And you can measure also the impedance of coaxial cable. So if you have a length of coax cable, you can measure its impedance using the antenna analyzer. That's how versatile your antenna analyzer is. It can measure the SWR of the antenna, and it can also measure the impedance of coaxial cable. Now, there's something you need to be aware of when you're using an antenna analyzer so that you don't get false readings. If you have a transmitter that's nearby, it could be your own, it could be another amateur radio operator, or it could be a commercial transmitter, it could be something where it's close to you and there's a strong signal, your antenna analyzer might give you an incorrect value. Because quite frankly, what your antenna analyzer is actually doing, it's actually a small mini transmitter. It's transmitting a small signal to your antenna, and it's measuring the reverse power that's coming back. And that's how you can measure SWR, for instance. But if you have a transmitter that's very close to you, strong, and you have that antenna picking up that signal and it's coming back, then the antenna analyzer will receive that transmission and think that the reverse power coming in is much higher than it actually is. So that's why we say that you need to be mindful. Strong signals from nearby transmitters can affect the accuracy of measurements when you're making that measurement on an antenna system using the antenna analyzer. So really trusty tool, really nice to have. Matter of fact, if it's when you become an amateur radio operator and you're getting into amateur radio work, this is probably one of the instruments that you want to get. All right. Yet again, test equipment, directional wattmeter. Well, what is that? So on the right-hand side, we have what a wattmeter looks like. So this is it here. It's a Bird brand, I think it is. You have connections, you have in and you have out. You have different parts to it. But this is how we actually connect directional wattmeter. So we have our transceiver of some sort. We have a piece of a jumper or a little piece of feed line here that goes to the antenna, the directional wattmeter. And of course, we have our coaxial or feed line, transmission line that goes to our antenna. And when we transmit, we look on the gauge of our directional wattmeter and it will show us how many watts of forward power is going, and then we can switch this usually and we can measure what our reverse power is, and we can actually calculate SWR using a formula with the reverse power and the forward power that's measured on your wattmeter. So that's why we say that a directional wattmeter can be used to measure SWR as well. You measure the forward power and you measure the reverse power and you plug it into a little formula and you can see what your SWR or your standing wave ratio. And it's all about making sure that you have a good match with your antenna. It's most important for maximum efficiency and to avoid damaging your transceiver. Yet another piece of test equipment that can be used by an amateur radio operator. It's called a field strength meter. And what do we use it for? Well, we use it to make antenna adjustments. We transmitter adjustments and antenna measurements. So for instance, here's one of the things we can do with our field strength meter. So on the right-hand side here, we have an example of what a field strength meter might look like. Little antenna, you have a gauge here, and you can walk around with this and you can see the strength of the transmission, the signal strength from an antenna. You could walk around and see at any point in time when you're walking around that antenna what the field strength is. And you could actually plot that field strength on a graph. So if you look here on the left-hand side here, we have our antenna that's at the center, and we have someone that's just walking around the field. All right, this is where our antenna is located here, and we're just walking around with this field strength meter. And we're saying, okay, at this point, that's the signal. At this point, that's the signal. And we just plot it on a graph, and we can see, for example, this Yagi antenna, this directional antenna, for instance, if I were to walk around the yard with this antenna as my test antenna and I have a transmitter that's transmitting, I might find, look how strong that signal is in this direction, but look how relatively weak it is towards the back. Remember we said that these directional antennas had front to back ratio gain towards the front. So you have a strong signal in this direction, but a weaker signal off to the side and to the back. So that is what a field strength meter can be used. We can adjust our antennas accordingly. If we find it should be stronger, we can make antenna adjustments and so on. And we can also determine what the radiation pattern of the antenna is by using the field strength meter. We plot it on a diagram like this, and this is the antenna radiation pattern that we are seeing in red here. We have the front lobe, we have the back lobe, and the front lobe is very strong, back lobe not so much, a little bit of signal towards the back, and that's one of the uses of our field strength meter. We also have a test that we can do for our transmitter. It's called the two-tone test. Now the trace here on the right hand side, using our oscilloscope, we are seeing two tones that are generated on this scope, and this is what we are trying to achieve. With the two-tone test is actually used to determine whether or not a transmitter, or this is a transceiver here, it has a transmitter stage, whether or not the operation of it is linear or perfectly linear. And that is what we want. We want it to be ideally linear. And to do that test, what we do is we inject two tones. So for example, in the left-hand side here, you see some software. And that software, what that does, it can actually generate two tones, and you can use these slider bars here and choose which frequency you want the first tone to be and what frequency. These are audio frequencies we're talking about here, because we're talking about tones, things that we can hear. And you can slide and select. Now, typically, you'll use around 700 hertz and 1900 hertz as the two tones. The important thing about the two tones that you're using for the two-tone test is that those two tones must not be harmonically related, or we say non-harmonically related audio signals are what you use when the process of doing the two tones. So you use, let's say, an instrument, or you can use software, computer with a sound card, and generate these two tones. And we're selecting 700 hertz and 1900 hertz. That tone goes into your transmitter or your radio, and then it transmits out. Notice here I'm using a dummy load with a tap, and then I monitor. I look at what that signal looks like. Remember, we said it's important. Do not connect your transceiver directly to your oscilloscope. You have to attenuate the signal in whichever way you do. So that attenuated signal is what we observe, and we see a nice clean scope, and then we can say yes. As a result of what we're seeing, we are injecting two non-harmonically related audio signals, and we're getting a nice scope view, and we can conclude that the transmitter's performance is perfectly linear. That's the two-tone test. So we also come now to transmitter interference. The reality is, as a ham, as an amateur radio operator, you do have the potential to cause interference. Yes, you can. Why? Because you are transmitting. And part of the training, part of what we need to know as amateur radio operators is how do we minimize, how do we reduce, how do we remove completely that interference, because we may be interfering with someone's cordless telephone, or we may be interfering with a television set, or something else when we are talking on our transmitter, when we are using CW, we're sending Morse code, and next thing we're interfering at someone who's looking at their favorite television station and their, or radio, or they're talking on the telephone, and we are causing interference. So we need to be aware as hams. There is the potential to cause it, but guess what? We are not going to, because we are trained. We know about the types of interferences, and we'll come very shortly as to how we can actually reduce that interference that we may otherwise cause. That's why we become licensed hams, so we know how to stop the interference. So we need to know for the exam that if you are transmitting SSB, single sideband, phone transmission, and remember, when anytime we say phone in amateur radio, we're talking about voice, meaning speech, we are talking. So when you have a single sideband phone transmission, it can cause interference to a nearby audio device. So for example, a telephone. But how will you know it's interference from your SSB transmission? What will happen is the person will hear a sound and it will be distorted. Whatever, let's say they are hearing someone else talking to them on the telephone, for instance, or someone is using a radio and listening to it, they may find that the speech that they are listening to becomes distorted. So then you can conclude, all right, it's probably my SSB transmitter that is causing a bit of interference. SSB transmission voice will cause distorted speech on the nearby audio device. But what if I'm doing CW or Morse code, and I'm using a CW transmitter? I'm sending my dits and das, and I'm causing interference to a nearby audio device. How will I know it's my CW that's causing it? Well, the person will say, well, you know, what I'm hearing is a sort of on and off humming or clicking sound. That's the consequence. So that's what's observed if our CW transmission happens to be causing interference. They will report to you, hey, I'm hearing on and off humming, or I'm hearing a clicking sound. And you can conclude, all right, it's probably my CW transmitter. And there are things that you can do to reduce or eliminate that interference. Now, again, like last class, we are going to go a little bit over because we're trying to cover quite a lot of material in our slide deck. So be prepared to go for at least additional 20 extra minutes beyond the normal time. So I hope that is okay with all of the participants. So we did say there are ways that we can reduce interference. And sometimes that interference we cause with our own selves. And sometimes if we're causing it to someone else, we can help them solve that interference that we maybe happen to cause to them. So we need to be aware that there are ways, many options to reduce that interference that our transceivers, our transmitters can cause to audio devices. The first one is called a bypass capacitor. And you may recall in the technician class as well as the general class, early sessions, we talked about capacitors, what they do, how they're made up, what they're used for. And that is one technique that you can use to reduce radio frequency interference in audio devices. You put a bypass capacitor, sometimes it's called a decoupling capacitor, in the circuit. And notice here you have that interference. And when you put that bypass capacitor, guess what happens? You just get the signal. You don't have that set of interference. So for the exam, you need to know that one of the ways is that you can install a bypass capacitor to reduce RF interference to audio frequency devices. So anything that you're listening to audio on, you're hearing something coming through a speaker and you're getting interference, a bypass capacitor is one of the tools and techniques that you can use. There's another one as well. We would have come across this in a previous session, Ferrite Chokes, when we were talking about toroidal cores and so on. So we can use a Ferrite choke around the cable to reduce the RF interference that is caused by common mode current on the audio cable. So on the right hand side here, notice you have your little iPod, earbuds and so on, and you might be hearing that interference coming from an amateur radio transmitter. It could be someone in your household, it could be a neighbor nearby. Well, notice here we can put that Ferrite choke. We wrap the cable around it. We wrap this around the cable, and that common mode current that is caused by our transmitter could be reduced or eliminated by using the Ferrite choke. And this is what one looks like closed, and this is what it looks like open before we wrap the cable around it, or we wrap it around the cable. So those are two techniques as hams. And notice we are training on how we can reduce transmitter interference, bypass capacitor and Ferrite choke. Another way to reduce transmitter interference, we have grounding. So we'll be talking a bit about grounding and bonding. We'll be talking a little bit alluding to electrical and RF ground. But grounding is very important as an amateur radio operator. And we need to learn what proper grounding is. We need to know the technique. Why? Because proper grounding can and does reduce interference. So first concept we need to know, and we need to know for our exam, is that all ground conductors should be connected to a single point. Why? To avoid a ground loop. So if we look at our bottom diagram here, notice we have A and B. A is actually putting all of the conductors to this single point, and this is correct. Notice the incorrect way, or the method that is going to cause a ground loop, and a ground loop is not good. You can have a lot of problems with a ground loop, which we will see in a little while. So notice the correct way. We want to connect all our conductors, all the ground conductors coming from our radio. This could be our radio, this could be our antenna tuner, this could be our, so I should say, amplifier, and so on and so on. All our equipment, this could be our computer, and we are connecting all of the ground connections from each device to a single point. And the reason we're doing that is to avoid a ground loop. If we do it incorrectly like this, and we have each item going to a ground like this is incorrect. This should not be. We need to bond actually, but this is incorrect. We have ground loops going on here, and that causes a lot of problems. One of them is that you can get a hum on your transmitted signal. So if you are transmitting and a radio operator say, hey, I am hearing a hum in your transmission, it could very well be that you have poor grounding or improper grounding, or you did not use the proper grounding technique, and you have a ground loop, and therefore the receiver, the person who is listening to your transmission, you're speaking to them, and they tell you you have a hum. It could be because you have a ground loop. So that's one of the symptoms of poor grounding or not grounding in a proper way. And here comes the part that, as hams, why we train, why it is that we need to know about these things, because guess what? You can zap yourself, you can burn yourself. There are things that you can do if you do not ground your station properly. So if you improperly ground your station, one of the effects is that you could have radio frequency voltages very high that's present in your station. So for example, this is your radio, and you might actually touch your radio or your power supply or something else, and if it's not properly grounded, you might get an RF burn, which is not nice at all. So you need to be aware of that. that because, let's say, the same ground loop that we're talking about here, that ground loop actually operates like an antenna, and therefore your station equipment could actually be transmitting, and you might have a high RF voltage on your equipment because your antenna is like a loop antenna. Your equipment is part or makes up a loop antenna, and you don't want your equipment to be the antenna. You want the antenna to be the antenna. Your equipment, your radio, your tuner, your amplifier, that should not be an antenna. But when you have ground loops like that, it actually acts like an antenna, and therefore you have, remember radio frequency, you have voltages and current. It's an electromagnetic wave. So because it's electromagnetic, you have current and voltage present, and that's actually how RF works. You don't want your equipment to be part of the antenna at all. And if you don't ground properly, your equipment might be, and you might be susceptible to high RF voltages present on your radio power supply. And you touch it, zap, there you go. You could have a nasty burn as a result. So be careful when you're grounding. You do not want to burn yourself when you're transmitting. When your transmitter is transmitting, you're not properly grounded, and you have a loop, you might get a burn. Now, what occurs there is that a high impedance on your ground can also cause that, because what it means is the frequency that you're transmitting on, because the high impedance to that particular frequency is what causes that RF to be generated. It acts like it's resonant, and therefore it acts like as an antenna, as a loop antenna, as a matter of fact. And that is when you will get the RF burn. So you need to know all of these points here for your exam. Proper grounding is important. So I did say we're going a little over, maybe about 15 minutes or so. So let's continue. Grounding and bonding. So it's two separate things, but they are very closely related. And this is actually a point of contention, and it's a point of confusion. Often people who discuss electrical theory, amateur radio operators. So let me see if I can help demystify what's the difference between bonding and grounding, or between grounding and bonding. Some people say it's exactly the same thing. All right, fair enough, you can say that. But really, we need to understand conceptually what bonding versus grounding is about. And it's the same thing in a way, but let's define what they are about. They are closely related. First of all, every metal enclosure on your station, so this could be your radio or your transceiver, you have a power supply that may be connected, you may have an antenna tuner, you may have an amplifier. First of all of the items must be grounded. That's the first point as a ham. If you do not do that, hazardous voltages can appear on the chassis. That is what could occur if you do not ground your station properly. Remember we said earlier that you don't want to get an RF burn, you don't want to get a zap, so therefore you must ground every single item in your shack or in your amateur radio station. Also, you need to bond the items as well. So you have grounding of it and you have bonding of it. And the reason why you want to bond it is to minimize what we call RF or radio frequency hotspots. So the solution to avoid RF hotspots is to bond all of the equipment. So let's look at the diagram on the right hand side and spend a few minutes talking about the difference between grounding and bonding. Let's dissect this diagram a little bit. So first of all, our ground connection is shown on the right hand side. There's a ground rod that goes into the earth. And by the way, in your station, all ground rods should be connected to each other. You should not have an isolated ground rod. That is not correct according to the NEC and most electrical codes. So anyhow, you have your ground rod in your station. It's usually outside, not too far from the shack or the house or the location wherever you're at. If it's a portable operation, you drive that ground stake into the ground, and that is your ground. But you must have that connected to a bar. This bar here is a common point where you will connect all of your equipment to. So this could be a copper strip, it could be a copper pipe, something really a good conductor, and you connect using a strap. Now these connections here are not antenna connections or power connections. This is a strap that you connect to the chassis or the body or the enclosure of the metallic equipment, and you connect it to a common strip. And doing so, when you connect all of them to the common strip, is called bonding. Each item on your shack is connected to each other via this strip, and that is considered bonding. You have actually just bonded all of the equipment together. You haven't grounded it as yet, huh? You are now just bonding the equipment, every single item, to this common rail or this common copper strip or copper tubing via these straps. You have just bonded all of the equipment. Notice your computer, your PC, your radio, your power supply. You have other accessories, maybe meters. It could be a tuner, it could be an amplifier. All of these items are bonded together. When you have done that, you then take another strap from that to go to your ground. Notice we didn't take a strap from the accessory to the ground, and then one from the power supply to the ground, and then one from the radio to the ground, and one from the PC to the ground. We did not do that. Remember we said the last slide, if we do that, we might have ground loops. What we do, we bond everything together, and we're doing that for RF purposes, but also for electrical grounding, because we ground that strap or that bar using this heavy gauge braid or cable to our ground. And that is grounding and bonding, and you must do both. Okay. So we can give interference, but guess what? We can receive interference too. Yes. As amateur radio operators, other things, other people, other equipment, other items can cause us stress by giving us interference. You are tuning your radio on a particular frequency, 14.245, and you're hearing noise around the band. If you look at this frequency, you see 3.785, and one set of noise all over the spectrum. Well, we need to be aware that one of the common reasons that as amateur radio operators, you turn your radio on, you have a beautiful spectrum scope here, you're looking at your waterfall, and you're seeing a lot of signals, and you think it's signals, and you realize when you tune to it, it's a set of noise. You're not hearing anyone, and you're not hearing any digital signal, it's just a set of noise. What sometimes causes that noise or that interference across a range of frequencies is if something is arcing due to a poor electrical connection. A very common one that happens sometimes is electrical poles. If you look at, you have the transformer, sometimes you have a little arcing going on at the connection, and that arcing at the electrical pole transformer can result in a lot of noise across the wide spectrum. But you can also have items in your home, in your house. You may have a receptacle outlet, or what we sometimes call a plug, on the wall, and that connection is poor, and that is causing some arcing inside of here. You don't even know it, and you have a set of noise on your radio, and it's difficult to receive transmissions, difficult to hear. So you need to be aware as a ham that a poor electrical connection that causes arcing can cause interference across a range of frequencies, making it very difficult to receive, and that's electrical noise. But again, guess what? For every problem, we have a solution. One of the things that you can do if you have that sort of noise and you have a DSP or a digital signal processor type IF filter, that's a feature of your radio, you can engage it, you can employ it, you can use it to help sort of reduce or remove some of that interference. And we need to know for the exam that if you have a digital IF filter or a DSP IF filter as opposed to an analog filter, the digital IF filter has a wide range of bandwidths and shapes that you can use to remove a lot of interference. So those are features, and we have some screens here showing those DSP type features that you have access to with the modern type radios, that you may have a digital signal processor type filter in your radio that you could turn on and tune, and you have a set of settings. You can shift things all over the place, you can narrow it, you can widen it, you can move it left, move it right, and you could create all sorts of shapes. That's what I mean here by that other point. A wide range of filter bandwidths, the width of this bandwidth, as well as shapes. So you have it narrow, you have it wide, you can move it left or right, and you can eliminate some of these noises that you would otherwise hear. So an advantage of a DSP or digital signal processor type IF filter when compared to analog filters. These are solutions to the noises or electrical noises that you might get from these sources. All right, just a couple more slides. So also, as hams, we need to be efficient and effective in using our transceivers. And one of the features that could be built in, sometimes it used to be an external device, but today you can get them built into transceivers. Sometimes it's an option, a board that you install. It's called a speech processor. What a speech processor is a feature, a circuit that helps you to increase your intelligibility or understandability of voice signals, especially when you have low signal propagation or what we call poor conditions. If you use a speech processor, your signal might be heard a lot better. We have a diagram on the right-hand side here shows us what unprocessed speech looks like. And then we have processed speech on the right-hand side. Notice that the signal is more compared to the unprocessed. What it does, it compresses some of these highs so that you could have more of these lows coming across. So overall, the average power is greater. If this is your speech and you send it to your transmitter, your average power becomes lower because notice you have these nice little high peaks, yes, but the rest of your voice is down in the doldrums here. So therefore, your transmitter is not going to transmit at full power or as much power as it can. But when you do that compression and you take your peak down a little bit, all of a sudden now, these lower frequencies here that you have, all of a sudden now, these frequencies, notice the amplitude, they are higher. They're shorter here, but they are higher here. It's the same speech, but you pass it through your speech processor. And because of this compression, what you find is that you have more speech going to your radio, and therefore your signal, your transmitter, is sending out a higher average output power, just simply by changing your speech. So imagine that as a trained amateur radio operator, those of us who are probably already licensed and never use speech processor say, oh, right, that's what my speech processor can do for me. I am going to use it now. So hopefully that has helped someone already. And as budding amateur radio operators, when you're purchasing your next rig, find out, do you have a speech processor inside of there that you can do this compression that we're looking at here? Because it can help you be heard when the conditions are poor. Remember we talked about the sunspot cycle the last time? When we are in poor conditions, we need to get every single watt out. And one of the ways to do that is to make sure we drive our transmitters efficiently without distorting. And that speech processor is what will compress the audio to allow us to have that maximum transmission or maximum transmitter power. So what we say for SSB phone, and remember anytime we say phone in amateur radio, we're talking voice, single sideband voice signals. They are affected by the speech processor by increasing the average power of the transmission. That's exactly what we showed on the diagram here. The average power is much less here. Notice most of the signal is low. But when you look at it here, most of the signal is high. It's wider, it's bigger. And because of that speech being wider or bigger, your transmitter output is also going to be higher average output power. But like everything else, if you are not properly adjusted, you can have problems. You can actually cause more problems with a speech processor than you solve. So you need to know, we need to know how to correctly adjust it. And if we do not adjust it correctly, here's what could result. Distorted speech. You're overdriving and you're sounding horrible, you're sounding terrible. No one will want to talk to you when you're sounding like that. So you have distorted speech. You can have splatter. That means you're transmitting spurious. You're all over the band other than where you need to be. And then, of course, excessive background pickups, meaning that you're getting all sorts of noise. Some insect in the corner that's making a noise, all of a sudden you're getting that. Or there's some car that's passing in the background on the roadway by you, and you're picking all of that up if your speech processor is not correctly adjusted. And you need to know all of these points for the exams. One more slide, folks. Okay, so on our rigs, on our transceivers, on our radios, we have a gauge that you can find on the radio. It may or may not look exactly like this, but this is one example of what these gauges look like on your radio. It's called an S meter. It's actually, sometimes you will say it's a signal meter. S meter is the common term, and it measures signal strength of the received signal. So when you are receiving a signal, if the signal is low, you'll have a low S number all the way down here. But if we have a very high or very strong signal, our needle, and this is our needle here in the diagram, will be much higher. So you have a strong signal here. Notice it's over plus 20/9. So it's a very strong signal that we'll be seeing here on our S meter. And we need to know that the S meter which we can find on most transceivers, measures the received signal strength. That's what the S meter does. Of course, it can do other things as well, but for our purpose for exam, we're talking about it just showing, and that's why I actually truncated the, just to show the S part, the signal part, received signal part of the S meter. Before truncation, there are other things like output power, ALC, and all sorts of other things on this gauge, but we are interested at this point on the S meter part of our gauge. Again, we also need to be aware that our S meter is not linear. The scale is actually logarithmic. So when you go from 1 to 2 or 1 to 3, it's not the same amount as going from 3 to 4 or 3 to 5. It's much smaller when you go from 1 to 2 than if you were to go, let's say, from 5 to 6. The increase from 5 to 6 is a huge increase compared to going from 1 to 2. So as you go up in the scale, it's just like those of us who may be familiar with the seismic scale. You know, you say you have a magnitude 2 or 3 earthquake. So if you go from a magnitude 2 earthquake to a magnitude 3 earthquake, the energy is not that much. But if you go from a magnitude 5 to a magnitude 6, even though it's still one digit above, one number above, that's a huge increase with seismic waves going from 5 to 6. Very, very large. Going from 1 to 2 or 2 to 3, that's relatively small. So that's what we mean by a logarithmic scale. The numbers are not linear. 1 to 2 is not the same as 5 to 6. 5 to 6 is several order times larger than when you go from 1 to 2 because it's logarithmic. We also need to know that whenever we go up one S unit, when we go from 1 to 2 or from 2 to 3 or from 7 to 8, any one S unit, you are actually increasing the gain by 6 dB or multiplying that power by 4 times. So even though it's a 1 S unit increase, you're actually multiplying by 4. So 1 to 2 is a 4 times increase. When we go from 2 to 3, we multiply that by 4 as well. And that is how it goes in terms of the amount of power. So we say it's a 6 dB. Those of us who may recall from our technician class, we did the decibel and showed what the decibel is in terms of gain as well as reduction. We showed it's not linear at all. It's logarithmic. And we're talking about the same thing, decibels. 6 dB gain for every S unit. And notice the S units, after 9, you have 20 over 9. So this is plus 20 over 9. And we need to know that 20 over 9 is actually 100 times. How do we get that? So we have a trusty little table here that reminds us of dB gain. A 3 dB gain is twice the amount of power. A little while ago, we said a 6 dB gain is 4 times the amount of power. When you have a 10 dB gain, it's 10 times the amount of power. But notice a 20 dB gain is 100 times the amount of power. And you'll get this in the exam. When you go from S9 to 20 over 9 as they call it, or 20 dB over 9, or plus 20 dB over 9, that's 100 times increase. It's not 11. You would say, well, 9 and 11 is 20. It's 11 times. No, it's not. It's actually 100 times. Again, that's sticking with the logarithmic concept. Remember, we said as we go up in the scale, when we go from one number to the next, it's several order times higher. Lower numbers, it's a small increase as we go up. So that is exactly how logs work. So you need to know this for the exam, that a signal that reads 20 over 9 results in a signal that is 100 times stronger. So you don't need to remember this table, but we just showed here. Anytime you think 3 dB, it's twice times. 6 dB, it's 4 times. 20 dB, 100 times. And this is a question that you'll get in the exam question pool. What does 20 dB over S9 means? It means that the signal is 100 times stronger. So folks, thank you so much for the extra time. We have come to the end of today's session. Just a reminder we keep getting new persons in the class all the time. And we encourage you to review the technician class sessions. tech.ttreact.com is the link. And also, if you need to register and you want to receive the text messages or the emails that will go out with all of the notifications, you can do so by going to this link here, general.ttreact.com. And folks, our next session is scheduled for Friday next, God's willing, Friday the 13th of August 2021 at 8:30 p.m. Want to wish everyone a very good night. All the best. Thank you so much. Take good care, everyone. Okay. Good night to you there, Adesh. Good night to you also, Larry. George, have a good night too. Yes. Night, Ramzan. Good night, Avin. Natasha. Good night also. All right, Larry, good night. Oh, John, doing quite well. I didn't see that message. Doing quite well here. Trust you are fine too. Right. Roger, good night also. Marissa, good night. Jessica, good night also. Right, got your question there. Took it there, Ramzan, earlier. Sylvester, good night. Oh, thank you so much. Really appreciate that. It was fantastic there. I mean, not the same as usual. Hopefully when the things improve in due time, we can celebrate. But thanks a lot for the kind greetings there, Sylvester. Much appreciated. Adesh, you too. Bye. You keep safe. Correct, Adesh. 73. All right. Larry, good night as well. Sure, you're certainly welcome, Ramzan. You're welcome. All the best too. Larry, appreciate the kind feedback. Glad to know you're enjoying the information. Roger, you too. Have a good night and you be safe. Yes. Have a good weekend. Gary, do have a good night also. Take good care. Oh, Larry, you're still at work. Well, glad you were able to join us, notwithstanding being at work. That's really good commitment. Glad you're able to be here. Stay safe too, dear June. All the best. Hey, Mark, glad you were able to make it. Have a good night as well. Nice, man. Thanks a lot for the support. Larry, okay, gonna get some, right? Have a good one too, man. George, good night. You have a good rest too. Is it Nike or Nike? Not sure how to pronounce. Sorry if I like to pronounce people's name correctly. So Nike or Nike, just send me a little note, the correct pronunciation there. Do have a good night as well. Thank you so much. And Ian as well, you're certainly welcome. Certainly glad to share. And you too, have a good night. So everyone, take good care. Be safe.